So in this next example, we're going to look at the analysis of some overlapping regions. And this is a system I work on quite a lot personally, the gold palladium system, where we can have a rich and diverse range of chemistries in terms of the palladium species. So you can see we have one palladium species here, another palladium species here. But this palladium 3D region is superimposed on top of the gold 4D. And we can see the gold, we can see the gold 4D 3 halves peak here, and the gold 4D 5 halves peak is situated under this palladium signal. If we look at this material, this particular catalyst, we can see we have our gold signal here, binding energy of 83.4, and as you will have seen in some of the catalysis lecture, this is quite a common low binding energy observed on titania or TiO2. Our titania here is, as we would expect, 4 plus titania. Our oxygen, again, as we would expect, lattice oxygen, maybe some hydroxide here, or carbonate, something like that, or indeed part of a sol. And if we look at the carbon, we can see we have some quite a bit of structure here, high binding energy, peak of about almost 289, a main peak at about 285 electron volts, and some peak somewhere buried in here about 286.5 electron volts. This is actually part of a PVA or similar sol used to make these catalysts. We have little or no chlorine in the system, and if we have a look at the survey, it's exactly as we would expect. Where we have our titania, our titanium 2p peaks, our oxygen peak, our OJ structure up here, our carbon, and there's a little bit of nitrogen, so this actually might be a PVP type preparation, the fact that there's nitrogen there. And if I zoom in, we can see and expand, we can see our palladium region here, and again here's a close-up of the nitrogen, so we know what's in our system. Okay, and again if we zoom in, our gold 4Fs are down here, and here's some titanium peaks. Okay, so we know what we've got. There's nothing untoward in our system at all. So let's just create a few regions. So I'll just highlight all these and click the survey and click the Add Regions button. And it's put on some default regions, so let's just tidy those up a little bit. Okay, we got a background Shirley type, that's fine for this exercise, and an average width of 5, let's just change that to 4 for the moment, and expand over this gold 4F region. Let's do the same with the carbon, the oxygen. Let's just move those regions around as opposed to the default values that CASA has put in for us. And again, this palladium 3D, we can just tweak that a little bit. That seems to be okay at the moment. And again, just do the titanium. So we can see that if we select the regions and quantify, we can get our quantification, and we've got what we roughly expect. We've got slight excess of oxygen, which is unsurprising given that there was that extra structure to the high binding energy side. There's no chlorine, that's fine. Actually, we automatically put a region on there, we can just delete that. As I say, there probably is a tiny little bit. Okay, so what we really want to do in this system is quantify or extract information for two things. We want to get how much palladium there is, so obviously we have to account for this gold peak in here, so we can do this by fitting. There are other slight clever ways of doing it, but numerically rather than sort of spectral subtraction, but we'll just go with the fitting method at the moment. And we can also check, because the nanoparticles with this sol preparation are all below 10 nanometers. I think if I recall correctly, the range is somewhere in the region of 5 to 7 or 8 nanometers as a very narrow sort of distribution. So just recall, XPS is seeing the average signal, and therefore we're seeing the average signal of all those particles. Okay. So obviously any quantification we do, as we done just now, let's just repeat that for the moment. We can see we have 0.3% gold according to our quantification, and about twice as much palladium. But of course, we're taking this region as a whole palladium region, so we're actually taking into account the gold signal, and we know that's not good. Even if we were to cut this region and just encompass the palladium 3D, we'd still have to account for this gold peak with it in this area. So okay, so let's just put our background somewhere around there. So what we can do to quantify these spectra is use, for example, our knowledge of our standard spectra. So we obviously have things like this is a gold 4F and gold 4D spectra taken from a clean gold foil, and I've done a fit. Now it's not perfect by any means, but it does give us a good starter to actually fit our data, if I just copy those, within this peak model. So if I just paste those gold peaks in and just move them around, something akin to that, we can see we have our gold speciation there. Equally, we can go back to our gold 4Fs and oops, giving the game away slightly there. If we copy this and go to our catalyst, then we can paste that gold in as well. Okay. We can actually see, I'll discuss this point now, we can actually see there's extra structure under here. Now this could possibly be gold 1 or small gold particles. Here the bind energy around about 85. I would expect another peak around about 3.7 electron volts away from that. And we do indeed have structure in that area. What we actually have here, and we can show by other methods that there isn't any gold 1 species in there, or even gold 3, which would be higher again, is that this gold is superimposed on a background of the palladium 4S, if I recall. I'll just get the palladium. Yes, the palladium 4S sits in this sort of area. And of course we'll have two contributions from that. We'll have the 4S from the what looks to be metallic palladium, if we base it on our palladium 3D spectra, and also this higher binding energy palladium species, which is probably a palladium oxide or palladium chloride. Well, in fact, we know it has to be a palladium oxide because we have no chlorine in the system, so it has to be oxidic in nature. So just for simplicity's sake, we're just going to create a quite a wide peak here. So let's take this to be something like 8 for the moment. Let's just call this BG and palladium 4S, just so we know what we're talking about, and just 0 the RSF, and we're just going to fit that. We can see our gold has come in much better now, and we're only quantifying this gold signal. We're using this nulled, or this RSF of 0 peak here encompasses the background signal, of which there is some slight overtone from the titania loss peaks, and the palladium 4S here. So it gives us a much better accountability for the amount of gold based on the 4F. If we turn our attention back to the palladium 3D, we have our gold there, and we would expect this gold to quantify equally, or as within our levels of certainty in terms of relative sensitivity factors, background shapes, etc., to be 1-to-1 in ratio with the gold 4F, and that comes from our knowledge, as I said earlier, about the nanoparticles being in the range of 5 to 8 nanometers. So in the elastic mean free path of the 40 electron, we should be able to see in XPS the whole of the particle, the top, the middle and the bottom, if you like. Okay, so now let's add our palladium signals. We can do that by using the models that we created in the previous exercises in terms of the fitting palladium nanoparticles, for example, and we'd expect these to be nanoparticle-like given the size. So we can call up that data, whether we made a peak model for it or save that data, and fit that accordingly. So okay, I've now pasted in the models that we created for the metals, for the metal nanoparticles. You can see the line shape is that we derived previously, and I've also put in 2 peaks for the palladium oxide. Now again, these can be modelled from a bulk palladium oxide material. Palladium oxide is one of these materials which has some satellite structure just like the metal does. But as we're doing for the metal here, we can actually ignore those small satellites because they're going to, essentially with such low levels of these metals, they're going to quantify to 0, or if we want to be more accurate, something like 0.001 or something equally as crazy. So let me just highlight the colors here. So we can see them named. We have our gold 4Ds in red here. In the lighter green we have our palladium metal signal, and in this sort of darker green we have what we're assigning as, I've called it palladium oxide here, but let's just call it palladium 2+. It makes sense in these materials that it is indeed oxide. So we fitted this spectra already, so we sort of skipped that bit a little bit, so I do apologize, but we can see that we've used our parameters here that we've derived from our models previously. Again, if we go back to our gold, here's the background palladium 4S, which is set to -1 here with a 0 RSF, gives us our background, and there's our gold peaks, again coloured in red, similar to the palladium 3D. Now if we quantify on using the palladium 3Ds and the gold 4D, let's see how much gold we get. So it's the sum of these 2 gold 4Ds, and we can see we've got 0.17 and 0.11, so we've got 0.28 in total. Equally, our palladium metal, we can see we've got 0.2, and our oxide is about 0.1. So we have extracted some ratios out of those now. If we take the whole of our regions and components, you wouldn't do this because then really you're calculating the gold twice. You're knocking out the ratios in the for all the other elements. But just to show you, if you actually do this, our gold 4F comes in as 0.23, our gold 4Ds come in as 0.28. So we have 0.05 difference, so less than 0.1 atomic percent difference. So given our accuracy in terms of our background shape, our line shapes derived for the nanoparticles, etc., we have what I consider excellent agreement in terms of our quantification. And again, we can just double check. If we go back to our palladium 3D and then just 0 the RSFs for the gold 4D, so we're taking, although we're integrating this whole area, we're taking away, we're just concentrating on the areas of the green peaks in this case. And if we highlight our other regions and do quantify regions and components, again we can see we have 0.23% gold and our metal again 0.2 and 0.1 for the oxide. So our quantification in both 4F and 4D is virtually equal, as we would expect, and again gives us quantifiable data that we can extract from the data. The next set of data I want you to have a look at and play with are, again, is a gold palladium system, but this time based on an activated carbon. So we've got wealth of data again in this system. We can see there's no nitrogen, there's oxygen in varying concentrations. We've got our palladium, we've got sulfur in these. Our carbon, as we can see if I overlay those, is graphitic-like, or activated carbon-like, binding energy of about 284.5. There's gold in this system, and the palladium, there's gold in this one, and palladium catalyst 2, catalyst 3 again has gold and palladium. And we can see, if we overlay these palladiums, that they're normalized here, but let's just knock off the normalization. We can see, if we normalize at this point, that we have different amounts of what we will consider to be palladium 0 and palladium 2. Certainly not palladium chloride, there's only a small amount of chloride there. So again, we have palladium metal and palladium, what looks to be palladium 2. Now the challenge with this system is quantification because of this quite a large background. Now this background comes from a phenomena known as escalos, and we're more familiar with it as just loss processes within materials. So for example, you have loss processes in elemental silicon, where you might be familiar with the plasmon losses. And these are just sort of oscillations, electrons being transferred and losing energy, and etc. And we can kind of see this if we just go to the carbon support itself. So you can see there's no gold in this. There's our carbon, no chlorine. We'll ignore that palladium for the moment. No nitrogen, some oxygen, some sulfur, and we can see again from the survey there's just a little bit of sulfur, our carbon and our oxygen. But if we zoom in on the carbon peak itself, palladium has a binding energy of about 335 electron volts. So again, if I zoom in further, we're in this sort of region here. And what we can see again, if I extend into this region and expand, we have this large loss peak after the photoelectric event of the carbon, between about 300 and 330. And we can see we still have another bump here which decreases down from about 320, 330 down to about 380 electron volts. And if we look at the palladium region here, we can see this is the tail that I just mentioned, and here's that secondary bump, which is again a loss process, as I say, within the carbon. Now, we want to model this, and there's several ways we can remove this from the data. We could do spectral subtraction, but that can introduce artifacts if we don't do it good enough. We can try and pull out different peak models from these data sets, perhaps using PCA analysis. Perhaps we might need more data sets for those. But regardless, what we have, or what we consider in these systems, is that our carbon doesn't change. After all, this is a carbon support, and we're putting on our gold and palladium. We may not expect the electronic structure or the bulk electronic structure or anything to be perturbed by us introducing these small amounts of gold and palladium. So we might expect this loss structure to be very, very similar. And if we take the system which looks to have the most palladium, if we look at the survey, you can see the palladium region here. and compare it to that clean, or what we call, considering sort of clean carbon support, and zoom in, we can see that these match very nicely. So we don't expect any significant difference. So therefore we can model this peak shape, or this loss, with a series of peaks. So what we're going to do now is just model that background very, very simply by using some highly constrained peaks. Again, there are other ways to do this, but I find this to be relatively straightforward and simple, providing we're just cautious about how we apply differences or peak positions and distances and full width half maximums and so forth. So I've already created a peak model, which I'll just paste in and fit, and we can see this broadly fits the data. Excellent residual, maybe too good for this noisy data, but nevertheless what we may expect for pulse counted data, and we can just tweak the background and fit that. So again, we got a standard deviation close to unity, which is good for this data. So you can see I've coloured those. We now have a peak which covers our carbon loss structure. So if I take this and, well, let's just propagate our background to our other palladium spectra. Let's just turn off that residual, and we can see we have our background propagated. Just tweak it slightly, and again I'll call this the RSF 0 and I call this CBG, doesn't particularly matter, that was carbon background for this region. And what we're just going to do is just paste, I'm going to copy all that, and you can see what I should have mentioned is I've taken this first peak. I could take any of them really, but I've taken this peak which was put in first, fix this position because we're expecting these, or assuming these don't shift, and put everything relative to that peak. So we can see that our other peaks are plus 8.1 and minus 7.9 EV. I've constrained the areas and I've assumed the full width half maximum is the same in all. This is just to model that background. As I say, it may not be the most elegant way, but it's a way that definitely works. So we'll copy all that peak model, and we'll go to our Palladium here and we'll go paste, replace. I'll just bring our peaks down just to give us a nice head start, and now we can just start populating this with our sort of gold and palladium models that we've used already. So as we say, we've put in our models, and we can see our coloration here of our metals, our carbon loss, our gold 4Ds, and the what we're calling again palladium 2 plus palladium oxide. Now, if we quantify these, again we might expect 1-to-1 for gold. Now these are, I've already fitted the gold region here as well and put on regions for the other, or defined regions for the other elements, and I've also put in a peak which is just relating to the palladium 4S. Now if we quantify these, again we might expect 1-to-1 as we've seen previously. However, in this case we can see we actually have 0.16 gold for the gold 4F, and we have 0.1 for the gold 4D. Now that might say that our background modelling is incorrect, and indeed it could be right. That may be the case. It could say that, okay, we do have large uncertainty, so our quantification of the gold is perhaps better on the 4F than the 4D in this case, because if we go back to our spectra, we've got quite well defined spectra here, but our palladium is actually a little bit more perhaps problematic to pull out. Sorry, not the palladium, the gold is probably somewhat more problematic to pull out because we have a higher degree of uncertainty as it sits amongst the loss structure, and will probably be affected more so by the background. We can see our residual given this data is pretty good. There are some little bits and pieces or areas where it could be improved, but nevertheless it's a good first approximation. It wouldn't stop us getting pretty good palladium 0 to palladium 2 ratios, or indeed palladium to gold ratios.